Hello, welcome back. We're going to continue with compound interest concept, and in this lesson we're going to go through 3 examples. So stay tuned. We're going to solve for different variables. Okay, that is going to be different than the last lesson I introduced compound interest. Okay, the first question: how much do you need to invest in a financial product, GIC, ETF, index funds, mutual funds, or whatever, with a return of a 7.25 compounded quarterly to grow to $50,000 in 20 years? So let's actually review the compound interest formula. So this is the compound interest formula where A is the initial amount, where A is a cumulative amount, P is a principal amount, what you start up with. 1 is 1. We have R as a interest rate, and you have to put a decimal equivalent of the percentage. And N is a number of compounding period, and we have to figure that out. It says quarterly. We need to know what that is. And then T is the time, which is 20 years. So let's write up what we do know. So we have all the information that we need. What we are looking for is the initial amount that we invested. So we're going to plug numbers back into the formula, the compound interest formula, and then we're going to solve. Let's go ahead and plug in the numbers. And here it is. We plugged in all the values that we have for each of the variables in the equation, except for P, because we have to solve for P. So before we do anything else, you can do the math for the bracket and a squared, and then divide both sides for whatever this side of the equation, which is the coefficient of the P, is. We have to divide both sides by that. So let's go ahead and simplify. So when you go do the calculation of the bracket to the power of 80, you get 4.208120. Notice that I left 6 decimal places expansions of this value here because it still continues, but we do need to keep as many digits as we possibly can, decimal places as we possibly can, so we can make it very accurate. And when we do this, divide both sides by the coefficient of P, which is 4.208120, and then the initial principal amount. When you do the division, you should get 11,881, and then I'm going to round it up to the nearest cents, which is 79 cents. So this is the initial amount that you need to invest at the rate of 7.25 compounded quarterly for 20 years. That would actually grow to $50,000. All right, let's look at the second question. Here it is. This is the second question. Determine the interest rate of an initial investment of 100 grand that yields to $200,000 in 30 years, but this time is compounded semi-annually, and that's part A. And then we have to compare it to what is the interest rate if it is compounded annually instead of semi-annually. Okay, let's go ahead and actually write up the formula again and then plug in what is it that we have. So here's the formula, and here are the values for each of the variables that we have, and then what we are looking for is the actual value of R, and then we're going to change that to the rate. That means in this case, the final answer should be in percentage. Now notice that N is 2, and that's because of this semi-annually right there. Okay, let's plug numbers in and let's do some math. So the first step is 200,000, which is accumulated amount. We have the initial amount of 100,000, and then 1 plus R we don't know. N is 2, and then 2 times T is 30 years, and then 2 times 30. So we're going to polish that again. And to do this, you can right away divide everything by 100,000. So this would be 2 equals to 1, and then 1 plus R over 2 to the power of 60. Okay, you can easily do that. Now that you have this, here is the trick. Okay, you need to isolate the value of R, but R is inside of this bracket and is divided by 2. The first thing you have to do, you have to get rid of this 60, which is right here. Okay, so that is the problematic number right now. We have to undo that power of 60, the exponent of 60, so that we can go inside of the bracket and then isolate the r. To do that, the opposite operation of exponent is taking the square root. In this case is the 60th root. That's what you need to do, 60th root of 2. So let's do that and let's see what that value is for 60th root of 2, because on the other side you're going to get just the bracket coming out. So when you do the math, use your calculator, and sometimes every calculator is different, but usually you want to use this key in your calculator, and when you plug numbers in, you do 2 to the exponent of 1 over 60. That's what you would do, unless you have a fancy calculator where it can do the 60th root of 2 with one go. But if you don't, that's what you need to do. And you will get 1.011619, and again I'm leaving it to 6-7 decimal places. And now we're going to go ahead and do the math, and in this case we're going to subtract 1 from both sides. That's just easy to do, and then we're going to rewrite. So we have 0.11619 equals to r over 2, and then to solve for r you multiply both sides by 2, and then you get r equals to 2 times that value. I did make a mistake here. I should have had a one extra 0 in front, 0.011619. So this should have been 0.11619. So I actually made the correction here. But when you do the multiplication, you'll end up getting 0.02323. And I'm just going to wait, stop after that. It's actually, you can just round it up to 246 decimal place, you get that. And then to get the actual interest rate, you have to multiply that by 100 and then put a percentage in front, and that just will be 2. Let's say 32%. That is the annual rate compounded semi-annually for 30 years. Okay, so compounded semi-annually, that's what you're getting, and that's why the power of compounding comes to play, because it's very, very important, and that's where the growth comes. All right, let's look at part B of this, which is what is the interest rate if this was compounded annually? That means if n was only 1. So if n was 1, let's rewrite this and then calculate it and find out what happens. I'm going to go ahead and rewrite the formula with values inside of that formula, but n is 1, and then we're going to see what happens. And notice that everything will be the same, but instead of 2, you're just going to have 1. That means the exponent here is not going to be 60, it's just going to be 30, and then we're going to solve. Okay, let's do that. So when n is 1 and it's compounded annually, is basically n, which is in a denominator, that's just 1, and I just don't put that in there, and then the number of years just gets multiplied by 1, and that's not going to change anything, but that's what you will get. So in this case now, to solve this, instead of taking the 60th root of both sides, you have to take the 30th root of both sides, and let's do that and let's see what happens. So we're going to take the 30th root, if I can say that, 30 and 30, that's the index for the radical expression, and then let's see what we get. So you will get 1.023373 and continuing, but I stopped after 246 decimal expansion, and then you have to subtract 1 from both sides, so r will end up being 0.023373, and then if you round it, let's say up to 4 decimal place, that's what you will get. And remember, change that to the interest rate. You have to multiply it by 100 and put a percentage in front, and that would be 2.34%, and that is annually. Okay, so the same idea, but this is now annually. Now look at the differential between the two. One is 2.32%, one is 2.34%. The differential between the two, we're looking at plus 0.02 of a percentage. That's what that is. Okay, so that's how, if you subtract those two, that's what you will get between the values, and that makes a huge difference in terms of the growth, because even though it's not much of a differential, but in the long run, it adds up. Compounding interest adds up every time you're compounding because you're getting interest on top of interest repeatedly for 30 years. All right, so this is the lesson. I hope you found this useful. Comment, share, subscribe. Until next time, keep at it.